Okay, so let's try again. Once again, let's talk about physics in slightly curved spacetime. Okay, so we start out with a metric. This is the metric. So where's my pen? There we go. Okay, so this is the metric. It's given by, okay, so this is dt squared. Dt is time, or dx, dy, dz. Those are spatial components. This is time component. This little theta here is much less than 1. This is the gravitational potential. And we'll see y in, well, we can already see y, right? Well, let's, because when it goes to 0, we get flat space. Because when it's 0, this is -1, this is 1, this is 1, this is 1, and that is the metric in special relativity. In special relativity, let's calculate the trajectory of the motion of a free falling particle. Okay, so a freely falling particle must satisfy the geodesic equation, which is given by this. This is the covariant derivative. This is the forward velocity. We can now write it in the tensor form or in the one parameter form. And there's a special rule here, this one. This is true if and only if this is true, where p is the forward momentum. We can see y easily as I showed last time in the second part of this video. Okay, now let's write it in terms of this, in terms of the forward momentum. Okay, so in tensor form is this, in the one parameter form is this. Now let's restrict it to the zeros component only. So we only look at the time component. Okay, if we only take the time component, this becomes alpha becomes 0, mu beta doesn't change. Assume non-relativistic velocity. So that means p0 is much greater than pi. We know why, right? Because pi equals mvi. So this just means the vi is negligible. If we neglect all the special components by this assumption, then we get this equation here. Okay, now we have to calculate the Christoffel symbol. Christoffel symbol is given in terms of the metric. Well, this is so, and what our metric? Well, we have it here, right? So we have the metric written in matrix form. Is this? So you see it's just this, right? So because the t squared is over here, and if we take the due of the metric, it's just everything inversed. Okay. And now let's calculate the Christoffel symbol, which is, well, so we plug into this equation here, and a lot of stuff goes to 0 because g01 is 0, g02 is 0, this is 0, so everything is 0 except for g00, which is this. And once you plug everything in, you get some tedious calculation here. g00, 0 is this, and when we calculate the this comma 0, this means just derivative is respect to the zeros component, right? And let's see what else. It's just so, oh, and here this is using Taylor series. That's all. We'll use Taylor series again. So 1 plus 2 theta is just 1 plus 2 theta plus 4 theta squared plus right? Taylor series. Everybody in calculus 1 knows that, right? What I'm talking about. Oh, okay. And so once we have calculated our Christoffel symbol, we plug this in, and in non-relativistic velocity, we can assume p0 equals to m, because that's just the rest mass energy. Okay, so plug everything in. If the gravitational potential is independent of time, then the energy is independent of time, because nothing changes here. Okay, so that's how you do. So that's the zeros component. Now let's look at the special component. So for some alpha, alpha doesn't equal to 0. Once again, we plug into this equation here, and we calculate this, and once again we assume p0 is much less than. I'm sorry, this is the other way around. P0 is much greater than P0 is much greater than P alpha. Right, and this is what I'm talking about. Right, just plug everything in, and we get to this part here. Once again, we have to calculate the Christoffel symbol, and we use the formula here. We plug everything in. We once again observe that G alpha beta equals 0 for alpha doesn't equal to beta, and so that means we can simplify this to be only when alpha and beta equal. So this here is the crystal delta Kronecker delta. So that just means 1 if alpha equals to beta, 0 otherwise, right? So Kronecker delta. Okay, so plug everything in, then this observe this is equal to 0 because here, right? And once again, just some tedious calculation, and once again we use Taylor series to approximate it, and we get to here, which this is just the force of gravitational field in Newtonian theory. Now, why is this important? First of all, the second part shows that Newtonian theory can be derived from Einstein field equation, can be derived from general relativity. So this is where the second part is important. The first part, where we calculate the zeros component of our energy. Well, we know P0 equals to E, equals to energy here in the weak gravitational field. But we'll see later on that when we go to Strasbourg metric, this become different. That means if you have an observer, if a different observer would observe different energies, so that's the point of it. We'll see that in Schwarzschild metric, this is different. The energy, so that means if you have a rocket ship, you're going at near speed of light, near speed of light, the energy you measure is different, and it's one of those fascinating results of quantum mechanics, general relativity.